Good morning. Thanks to the conveners for organizing this session, and thanks to all of you in the audience for coming. I must commend you for your endurance for making it through AGU, and to commend your achievement. On the count of three, I want everybody to take a deep breath. 1, 2, 3. And respire. Okay, respiration. It's a conversion of chemical energy for our metabolic processes, and I think it's an underappreciated process in our reconstructing of the global carbon cycle, and hopefully you'll leave today with an appreciation for respiration and the role it might play in controlling the variability of the global carbon cycle. Okay, so this is a very complex puzzle that we're working on here, and there's many pieces to the puzzle. Those pieces have been described thus far by Peter and Inez, and there's lots of different pieces that we can use to put together this puzzle. So we've heard about atmospheric observations. I'm going to combine those with remote sensing data from MODIS, and also some flux data here from Niwot Ridge to gain new insight on how our models are doing at capturing processes in the global carbon cycle. So we're trying to move beyond correlations and move more towards processes and diagnosing those processes. Okay. How do I advance? Thank you. Okay, so this is a very provocative paper that came out recently from Peter Cox, and he identified this really strong correlation between tropical temperatures and interannual variability in atmospheric growth rate. And I read this paper multiple times, and it was really fascinating, and it really got me thinking, so what's controlling this? Is it photosynthesis, or is it respiration controlling this variability, or a combination of both? How can we tease this apart and move beyond this correlation and move towards identifying the processes that really control this? For instance, photosynthesis could be suppressed at higher temperatures, or respiration could be enhanced at high temperatures, and these would have the same net effect on the atmosphere. So it was a very intriguing relationship, and I thought, how can we tease this apart into different processes? So one way we can do that is by looking at another piece in this puzzle, which is the MODIS record of greenness, effectively. And this MODIS record of greenness can be translated into estimates of carbon, a currency that is more useful for us. So here is the classic synthesis from Namani and Keeling, where they compare the MODIS satellite record, or maybe this is the AVHR record, to the atmospheric CO2 growth rate over time, and notice a strong relationship. But hopefully I'll convince you that maybe what's most interesting about this figure on the bottom is what it doesn't show. Okay, so just a brief primer on the global carbon cycle. You've seen it already, but the dominant fluxes on an annual scale are the uptake by photosynthesis and the respiration, either due to autotrophic or heterotrophic processes in the terrestrial biosphere. So we're really going to focus in on those. So how can we tease those apart in a crude way? So this is the only equation I'll be showing, and thankfully it's easier for me to interpret. But it's a simple master equation that is familiar to most ecologists, and that's net ecosystem exchange here is a function of gross primary productivity, so the amount of carbon going in minus total respiration coming out. Very simple mass balance. what we can do here is we can use the satellite data to estimate the upper limit of the global carbon cycle, and we can use the atmospheric observations to estimate the lower limit of the global carbon cycle in an inversion approach. So what happens when we do this? Okay, so I just did this simple subtraction of the two curves. So here we have, once again, gross primary productivity on the top, showing an increasing trend over time, this significant increase over time. And most of the error around this term, it turns out, is due to climate data that's used in the algorithm to transfer this measure of greenness into a currency of carbon. And there's very little instrumental error by combining two satellite records here. But here we have 30 years of continuous data of gross primary productivity, and then here is the NEE term as inferred from atmospheric observations over time. And simply by taking the difference of these, I'm just doing an eddy flux, if you will, for the planet. What we're left is a respiration curve. And granted, there's a lot of processes that are lost terms in the global terrestrial carbon cycle. I would argue that the dominant flux is respiration, either through heterotrophic or autotrophic respiration. And if you plot this up, there's a few curious features here. So here's 87, where we get a peak in respiration, apparently. Here's post-Pinatubo, where respiration seems to drop. And here's the highest value in respiration in 1998. And then it's been relatively, it appears to have been flat. So we can look at we can fit a lot of curves to this using a Monte Carlo type approach and look at what's driven this acceleration of NEE over time. It has to be the planet taking up more CO2 from the atmosphere or losing less CO2 from the biosphere. And it turns out that this apparent acceleration over the warming hiatus appears to be due to a reduction in total respiration, which makes sense perhaps, especially if you compare that curve once again with land surface temperatures. So here's just land surface temperature anomalies in blue, comparing my total respiration curve, crudely calculated as the difference between the satellites and the atmospheric CO2 observations. But pretty strong relationship. This suggests to me that maybe respiration might be one of the key processes that's driving this variability over time. And there appears to be this unraveling over the warming hiatus where correlations fall off. So if we delve into this a little bit further, this is work by Bill Andrig, and he's trying to tease apart this relationship in the tropics. And although this relationship is not very strong, it is suggestive that minimum temperatures in the tropics on interannual timescales are controlling this respiration that Peter Cox originally, this variability that Peter Cox originally identified in his relationship. And Bill goes on to do some likelihood estimates to find that tropical minimum temperatures are perhaps active in that. So now, what do the models say with respect to respiration? So we can go into the CMIP-5 ensemble of respiration estimates over the last 30 years, and those are plotted as these colored traces here. And once again, that's my curve that you should recognize that corresponds to land surface temperatures. And you see that respiration accelerated for this warming period and then appears to have leveled off for this warming hiatus period. So if we look at the change over time, we see that the models are not changing through here, and those are these gray bars over here. That's the CMIP5 estimates, compared to our estimates. So this is a cumulative change in total respiration over the warming period versus the warming hiatus. And you see our estimate of total respiration has dropped off significantly, whereas the models just keep chugging along. And you see this dip here due to volcanic forcing, which is included in the models. But we wouldn't necessarily expect, if the models are missing the decadal variability in temperature, that they would then accurately predict the total respiration over time. So this simply demonstrates to me that there might be implications in the models. If they're unable to capture the temperature variability, they might not be able to accurately predict critical terrestrial processes in the carbon cycle. Okay, so I want to take the second half of this talk to talk about other ways in which we can use C13 and atmospheric CO2. And it turns out that the main fractionating factor of atmospheric CO2 is the terrestrial biosphere during photosynthesis. So as stomates take up CO2 from the atmosphere, they really, plants, the rubisco in plants really prefers the lighter isotope. So there's this fractionation that occurs. And this was probably evident too in Peter's curve, where he perfectly overlaid the C13 and the atmospheric CO2 when he scaled them, suggesting that the terrestrial biosphere is strong at controlling the fractionation of atmospheric CO2 and its isotopic composition. So we can look at the source of the CO2 to the atmosphere, and we do this through a mass balance approach. And we can do this at many different scales. So here's data from Dave Bowling at Niwot Ridge, where he identifies a strong seasonal cycle in the source CO2 to the atmosphere, suggesting less fractionation occurring over the seasonal cycle as plants become water stressed. And we can also correlate that, the fractionation of the canopy, with different environmental factors that we think plants are responsive to. And here he shows this really strong relationship with vapor pressure deficit, suggesting that stomates are responding as vapor pressure deficit goes up throughout the growth season. Stomates are closing and less fractionation is occurring. Okay, so we can play this game at the global scale too. Here's a global network of terrestrial sites. And if we do that on the terrestrial sites, we see the same seasonal pattern emerging. And I kind of like to call this figure my Keeling plot of the globe. And it shows a similar pattern of less fractionation occurring during the summer months in the northern hemisphere. So what's controlling that? If we look at it, it appears that vapor pressure deficit also controls these different sites and the amount of fractionation occurring at these sites, and maybe more so than relative humidity, which is interesting in its own right if you think about how vapor pressure deficit and relative humidity might change as Earth's atmosphere heats up. So that was the response of most of my colleagues was, well, you've identified this interesting relationship, but what implications does it have for the global carbon cycle? So as of late, I've derived a simple SIB model. So there's like a very simple biosphere model, and it's forced by GFDL future predictions of increasing temperature, increasing CO2 to 720 parts per million. And then I'm really interested in the relative humidity response versus the vapor pressure deficit response here. So looking forward in this model, we see very little change in relative humidity, perhaps an increase in variability, but a strong increase in vapor pressure deficit. So what is the response of stomates to either this no change in relative humidity and this change in vapor pressure deficit? So if we look at that, over time, I don't know if this is going to work here. What we see, if you do an animation of that, is you see a strong difference in the amount of carbon assimilation by the terrestrial biosphere moving forward. It can be reduced by vapor pressure deficit, and mainly this reduction occurs during this interval where CO2 is increasing in the atmosphere, and you see that assimilation does not increase as much if stomates are responding to vapor pressure deficit compared to relative humidity, using the same parameters, just having stomates respond to these different variables, suggestive that maybe the terrestrial biosphere can't take up as much carbon as we would hope. And there's many different factors that might control this slope of increase in assimilation, and people have been working on those. Nutrient limitation might affect the slope at which this assimilation increases. Other factors like temperature might diminish this slope. So this is just one of a number of factors that might begin to constrain the terrestrial biosphere's capacity to take up carbon into the future. Okay, so I just want to conclude by giving you a couple of key findings to leave the meeting with. So the net ecosystem exchange of carbon seems to be accelerating over the last 15 years, over this warming hiatus period. And I think we can use the warming hiatus as an interesting natural experiment, similar to the way people have used Pinatubo and other natural experiments in the Earth system to gain insight. And the insight that I think I've gained here is that that accelerating net ecosystem exchange is a result of decreased respiration. And then much of the interannual variability that Peter Cox has identified seems to be due to total respiration, at least based on our preliminary estimates. And isotopic source of CO2 can provide important information independent of the information that Peter has described in his talk. And that really is a key point to make, that we need to continue making these measurements because we never know what insight they might provide to future generations and future scientists. Thank you.
We have time for probably one quick question, if anyone has a burning question. Otherwise,
question here.
Go ahead.
I don't know if this one's working. I'll talk loud if it doesn't come through. In your slide, you showed CO2 growing to 720 parts per million in a couple of centuries. In Peter Tan's first talk, he suggested it would peak at 450 because we would run out of fossil fuel sources. Is there much agreement among the community? Is just how high CO2 is going to grow and when?
There's numerous different representative concentration pathways that the scientific community has come up with, and arguably an RCP pathway of 8.5 watts per meter squared forcing is not a trajectory we want to be on, and I think we're moving away from that trajectory. But there are a range of scenarios. My estimates are hopefully a little bit high, but I doubt we're going to level CO2 off below 500 parts per million. It just doesn't seem realistic at the rate we're going.